welcome to this lecture of polymer reaction engineering. In this lecture, we will discuss about the molecular weight control in the linear polymerization system. Then we will discuss about the molecular weight distribution in linear and non-linear polymerization. Now, before we start the discussion, let's have a look at that what we have studied in the last lecture. We discussed about the accessibility of various functional groups. We had the equilibrium consideration under the edges of closed and open system. We discussed about the cyclization versus linear polymerization with the possible cyclization reactions. We gave major emphasis towards the cyclization versus linear polymerization under the head of cyclization tendency versus ring size, reaction conditions, thermodynamic versus kinetic control. In this particular lecture, we are going to discuss the molecular weight control in linear polymerization methodology. In this particular head, we will discuss about the methods through which we can control the molecular weight in linear polymerization. We will give the quantitative aspect to those approaches. Then we will have a discussion about the molecular weight distribution in linear polymerization with respect to the derivation in the size distribution. Breadth of molecular weight distribution. Then we will discuss about the effect of reaction variables. Apart from this, we will discuss about the molecular weight distribution in non-linear polymerization, especially under the head of effect of functionality and growth of non-linear network. Now, let us start with the concept of molecular weight control in linear polymerization. So, usually in polymer synthesis, one is ideally interested in acquiring a particular molecular weight product, as the characteristics of the polymer being developed, they are highly dependent on the molecular weight, and that is why we always talk about the molecular weight distribution, number average molecular weight, weight average molecular weight, etc. Then these molecular weights are greater or less than the ideal weight, they are equally unwanted. So, there are many influencing factors such as reaction temperature, monomer concentration, closed type of system or open type of a system, effect of catalyst, etc. So, these are the various things those who are participating in the molecular weight control of those linear polymerization. Now, let us have a discussion about the methods for which the molecular weight can be controlled in linear polymerization. Now, one way is that by quenching the reaction, that is by the cooling at the required time, so that the temperature remain maintained and the desired molecular weight you can achieve. Now, sometimes this particular methodology offers a disadvantage. Now, the disadvantage is that the polymer achieved is unstable, as resulting heating contributes to the variation in molecular weight, since the functional group at the end of the polymer molecule can further react, and this is sometimes a disadvantage. And furthermore, another thing is that whenever you quench the reaction mass, in that case the polymer molecule may not have sufficiently strong with respect to the mechanical approach, and that type of thing is essentially required in the suspension polymerization type of thing. So, that is why this is a disadvantage. Now, another method is that by increasing one reactant over other, the polymerization then continue to a stage at which one reactant is fully used up and all the end of the chain have the same functional group, the group which is usually in surplus. The example of this particular type of thing is that the polymerization of an excess diamine with a diacid, this produces the polyamide with amine and group in the unavailability of the diacid for the continuous polymerization. Now, let us have a look about this one, that is H2N R NH2 plus HOOC, that is this one is in excess. So, this gives you the HNHR and HCO R dash CO NHR NH2. Now, the polymerization of an excess diacid with diamine produces same result, that is the polyamide with a carboxylic end group in the unavailability of diamine for the further polymerization. Now, this can be represented like this. HOC R dash COOH plus H2N, that is in excess. COR dash plus CONH R NH CO R dash COOH. Now, sometimes by addition of monofunctional monomer, the monofunctional monomer also referred to as a chain stopper governs and restricts bifunctional monomer polymerization. So, the developing polymer produces the chain ends that are lacking in functional group and thus unable to react further. Let us have an example like the polyamide synthesis. The use of benzoic acid creates a polyamide 11 with the phenyl group and group that are not reactive to polymerization. Now, it can be represented like this: H2NR NH2 plus HOOC R dash COOH plus phenyl group COOH. This gives CONH R NHCO R dash CO NH R O CO 5. Now, another approach is based on the quantitative aspect. Now, to better regulate the polymer's molecular weight, the stoichiometric ratio of bifunctional monomer or monofunctional monomer must be precisely balanced. So, by this way you can regulate the things. Now, if non-stoichiometry is too high, the molecular weight of polymer would be too small. Now, this is also essential in understanding every reactive contaminants quantitatively effect that may be initially exhibit in the reaction medium or is produced by involuntarily side reactions. Let us consider the different reaction system used in the polymerization. So, the first type of this one is that the polymerization of bifunctional monomer AA and BB, where BB group is in excess. So, the number of functional groups A and B usually they are given, and they are respectively given by the NA and NB. The number of AA and BB molecules is twice equal to Na and Nb. So, the stoichiometric ratio of two functional group is given by R is equal to Na upon Nb, that is either less than or equal to 1. Now, the total amount of monomer molecule is determined by Na plus Nb upon 2 or Na, if we utilize the previous equation, 1 plus 1 upon R by 2. So, the fraction of unreacted functional group is given by 1 minus P and 1 minus Rp. The total number of unreacted functional group is usually given by Na into 1 minus P and Nb into 1 minus Rp. So, therefore, the total amount of polymer molecule is determined by Na 1 minus P plus Nb 1 minus Rp by 2. The total number of average degree of polymerization dP bar xn is usually given by the total number of molecules initially present divided by the total number of polymer molecule. So, we can represent mathematically as by x bar xn is equal to Na 1 plus 1 upon r by 2 upon Na 1 minus p plus Nb 1 minus Rp upon 2, or 1 plus r upon 1 plus r minus 2 Rp. So there are two conditions. When r is equal to 1, then bar xn is equal to 1 upon 1 minus p, and when p is equal to 1, then bar xn is equal to 1 plus r upon 1 minus r. Now let us take one example, that is here you need to find the average degree of polymerization when the conversion is 100% and uses 0.98 moles of AA and 1.0100 moles of BB. So we know, let's solve this particular thing. So we know that R is equal to Na upon Nb, and that is 0.98 into 2 upon 1.01 into 2, that is 0.97. So bar xn is equal to 1 plus r upon 1 minus r, and that is equal to 1.97 upon 0.03, and it is referred to be xn is equal to 66, and that is my answer. So you can see here that this particular figure shows the dependency of average degree of polymerization on the stoichiometric imbalance R in the polymerization of AA and B with BB for the different extent of a reaction. So you can see here the stoichiometric ratio, mole percent, and then this the number average degree of polymerization. So you see that the variation of this P correspond to the different values. Let us have a look about the quantitative approach again. Now if we see the figure 1 that is represented in the previous slide, that 100% reaction stoichiometric ratio of 0.1 and 1 mole percent, if R values of 1000 by 1001 and 100 upon 101 respectively, the bar xn quantities are 2001 and 201. Similarly, at 99% it is 96 and 66, where 97%, whereas at 97% it is 49 and 40. Now to obtain the higher degree of polymerization, higher conversions and the acceptable stoichiometric ratios are always having an essential requirement. The precise combination of P and R values made to accomplish some specific degree of polymerization. Now let us have a look about the type 2 type of quantitative aspect. Now the monitoring of degree of polymerization by addition of a small amount of a monofunctional reactant to the polymerization of an equimolar mixture AA and BB. So similarly, if we talk about the equations which we discussed in type 1 type of approach, the mole of A group is Na by 2 and the mole of B group is Nb by 2. So the moles of monofunctional B is given by Nb. The stoichiometric ratio of two functional group is usually given by R is equal to Na upon Nb plus 2 Nb dash. Now let us have another example to cater the need of this type 2 system. Now here you need to find the average degree of polymerization with number of moles of A and B group. They are 1 mole in each number, and the number of moles of monofunctional group Rb is 0.01, where 100% conversion occurs. So you need to find the average degree of polymerization. Now see, here we are having R is equal to Na upon Nb plus 2 Nb dash as per the previous equation which we discussed over here. We can put all the values, so it becomes 1 plus 2 into 0.01, or it is comes out to be 0.99. Now bar xn is equal to 1 plus r upon 1 minus r, that is 1.99 upon 0.1, and that is bar xn is equal to 199. That is my answer. Now, when we talk about the molecular weight distribution in linear polymerization, now usually this polymerization, one major fact we need to address, that polymerization is a combination of polymer molecules of varying molecular weights. Now, chains with a wide distribution of chain length, they are found in a standard synthetic polymer sample. Now, this distribution is rarely symmetric and involves several high molecular weight molecules. So, particular polymerization parameters influence the specific width of the distribution of molecular weight. For instance, the polymerization of certain olefins can lead to the substantial molecular weight distribution. Now, Flory, he derived the molecular weight distribution through a statistical approach focused on equal reactivity of functional group. This is purely an assumption that he assumed that every functional group is having the equal reactivity. So, all unreacted functional group have equal opportunities at any point of polymerization to participate in the reaction, regardless of the size of the molecule to which it is attached. The probability that a given functional group has reacted after the conversion is usually equal to the distribution of all functional groups. Now, when we talk about the derivation of the size distribution, in that case, this is considerably that this derivation is considerably applied to the step polymerization having the forms of AA plus BB and AB. Now, this is associated with the possibility of having a molecule that has interacted with X minus 1 A groups and unreacted with at least one A group. The extent of reaction P is referred to as the probability that an A group has reacted at time t. So, the possibility that X minus 1 A group have reacted is P to the power x minus 1, where x is the structural units. This is the use are being used in that particular polymerization process. So, the possibility of a group being a group being unreacted is 1 minus p. Now, here you see that Nx is equal to P to the power x 1 minus P. Now, Nx is associated with the moles or number fraction of x moles in the polymer mixture. Similarly, Nx is equal to Np x minus 1 minus P, there N is associated. This N is associated with the number of polymer molecules. So, the overall amount of structural units initially present is N naught, that is N is equal to N naught 1 minus P. So, therefore, if we substitute the value of this N to this particular equation, then it is found that Nx is equal to N naught 1 minus P square P to the power x minus 1. So, the weight fraction Wx for x mer or mer is given by Wx is equal to x Nx upon N naught. Therefore, if we substitute all the values, the Wx is equal to x into 1 minus P square into P x minus 1. Now, to give the more pictorial view, the derivation of various size distribution can be expressed with the help of these two figures. Here we have represented the distribution curve of number and a weight fraction for linear polymerization. Now, in the plot, various lines like 1, 2, 3, these at P is equal to 0.96, 0.9875 and 0.9950 respectively. So, these number and weight distribution are commonly called the probable distribution or Flory-Schulz distribution. For several p values, the plots of these two things like polymerization versus number fractions and degree of polymerization versus the weight fraction, it is given over here. Now, when we talk about the molecular weight of number and weight average, it can be given as Mn bar is equal to W. This is equal to summation of Nx Mn upon summation Nx, and Mw bar is given as, this is the universal formula. Now, if we divide both the equations with the Mn, then Mx, then it is bar Xn is equal to Nx upon summation Nx, that is X and X, or bar Xw, that is summation Xwx. Now, sometimes it is quite significant that when we talk about these bar Xn and Xw, this which we can obtain, which we obtained in the previous slide from the function of number and weight distribution. Now, in that case, if we have these particular mathematical equation in question, now if we put the values of Nx and Wx from this previous equation, we may have bar Xn summation Xp minus 1 minus p, and X bar Xw is equal to summation X square p x minus 1 minus p square. So, on evaluating this particular equation, we may have bar Xn is equal to 1 upon 1 minus p, and bar Xw is equal to 1 plus p upon 1 minus p. The breadth of the molecular weight distribution, which is sometimes referred as polydispersity index, it can be given as bar Xw upon bar Xn is equal to 1 plus p. Now, let us have a look about the effect of reaction variables. Now, sometimes change in reactivity of reaction play a very vital role. Now, in a bifunctional group, the increased reactivity of one functional group to the other group contributes to overall increase in polydispersity index. Now, if there is a greater than a double rise in the reactivity, the polydispersity index reaches to a maximum conversion. Now, when there is a decrease in the reactivity of one functional group to the reaction to other group, the polydispersity index decreases, but PDI, that is the polydispersity index, at a maximum conversion is having 2. So, as functional group reactivity varies continuously with the molecular size, similar patterns are observed but are more exaggerated. Now, let us talk about the molecular weight distribution in non-linear polymerization. Now, using over two reactive end groups such as tri, sometimes tetra functional monomers, they produces step polymerization of non-linear polymer molecules such as over branched or a cross-linked polymer, and sometimes the dendrimers and dendrigrafts polymers. So, this type of approach is important while considering the various issues related to the non-linear polymerization. Now, dendrimers have extremely regular branching with strict geometric branching. The pattern typically uses a significant quantity of synthetic steps involving refinement after each stage, leading to low cost yield. Now, at a root, dendrimer's growth begins and proceeds radially outward from the middle of by adding monomer stepwise. So, in dendrimers, the attractive secondary forces are weaker than in linear polymer, since to attract each other the molecules do not pack efficiently. So that affects sometimes to the nature of these non-linear polymers. Now dendrimers do not have adequate strength of fibers and plastic, since no chain entanglement to exist in this type of dendrimers. Now with the other materials, the dendrimers have better solubility and miscibility, making them suitable as viscous additives. Now synthesis of hyper-branched polymers with structures that are less conventional than dendrimers, it can be performed using multifunctional type ABN monomers, and where you may have n is greater than or equal to 2, or through merging linear multifunctional monomers such as AA and B3. Now crystallization, this can be prevented by branching in over branched polymers. So these can be used as a functional additives for cross-linked polymers. Now adds, adhesives and a coater sometimes play a vital role in the linear polymerization system under the edges of molecular weight distribution system. Now linear molecules like AB or a mixture of AA and BB, and the trifunctional cross-linked molecules like AB2, A3, B3, they may be used to generate the cross-linked configuration. Now let us talk about the functionality. Now multifunctional monomer molecules can have this specific type of functional groups like A3 or various forms of group like AB2. So the average functionality of the analysis of polymerization kinetics for multifunctional monomer is usually defined as the average number of functional groups per monomer molecules. So it can be represented like this, F average is equal to summation Ni, where Fi is the functionality in reacting mixture of monomeric species. Now if the initial and the total number of molecules is represented as N naught and N at time t, then N naught F average is the number of initial functions. Therefore, the functional fractional conversion is given by P is equal to 2 N naught minus N upon N naught F average, that is equal to 2 upon F average 1 minus N upon N naught. Now dPn, that is the degree of polymerization, is given by N naught upon N, 2 upon 2 minus P F average. Now if F average is 2, when there is a AB monomer, then dPn is equal to 1 upon 1 minus P. Let us represent that this is equation number 1. So in the non-stoichiometric type of system, that is Na is less than Nb, no reaction can take place after the A group is fully finished, and it is convenient to think of the limiting functional group instead of the total conversion. So in this case, the average functionality can be defined as the total amount of functional group that can react divided by the number of molecules initially present in the system. So from the previous equation which we discussed over here, the degree of polymerization tends to infinity as P is equal to 2 upon F average. Therefore, if F average is greater than equal to 2, the limiting functional groups conversion is reasonably high, the average chain length of the number becomes infinite and the polymer gelation occurs. Now let us talk about the growth of non-linear network, because non-linear network, the development of non-linear network is again important aspect. Now considering the combination of two bifunctional group AA and BB and a trifunctional monomer, that is A3, to a further investigation of growth of branched polymer network and gel molecules development. So, P.J. Flory, he identified a chain or a section of a branched polymer as a segment of a molecule among two separate units or branch unit and an unreacted terminal functional group. So, the structure of structure of a chain from branched polymer between two branches, this can be represented as AA plus AA plus BB. Now, here this can be BA, A, now the probability, sometimes we may have to look into the probability, we will discuss sometime later in this particular approach. Now, before we go into the probability approach, let us discuss that the Flory suggested the assumption within which there be a finite probability that any chain product or selected randomly from the reaction mass would appear as a part of infinite network. The branching coefficient alpha usually is based on the probability that a specific functional group contributing to a branch group, usually it contributes to another branch group. Now, assuming the equal reactivity of all functional group as we discussed previously, the following variables you can define, like PA is a functional group of A has reacted along the chain. Let us see first that what equation we are proposing. The probability for the linking of a group of a branch unit to the series of unit, and this can be represented as PA, PB into 1 minus P star into PA, I, PB, P star. Now, here PA is the functional group A has reacted along the chain, PB is the functional group B has reacted along the chain, P star is the ratio of A, that is reacted, whether reacted or unreacted group on multifunctional cross linkers unit, divided by the total number of groups of A in the initial reaction samples. So, these are the usual notations. Now, similarly, the probability for another randomly selected group on a branch unit that may consist of a multifunctional monomer would contribute to other branch units through a chain or any length is usually given by alpha summation I is equal to 0 to infinity PA PB 1 minus P star PA PB 1 minus P star PA minus 1 PB P star, or this can be I is equal to 0 to infinity PB PA 1 minus P star PA I PA PB star, or this can be PA PB P star upon 1 minus PA PB 1 minus P star. So, here the PA and PB, they are related as PA upon PB NB naught upon NA naught. So, the initial moles of functional group A and B are NA naught and NB naught respectively. Now, these equation can be used to solve the critical values for the conversion of limiting functional groups. Now, in this the last when we sum up that particular chapter, Then at last in the conclusion that we say that the molecular weight distribution play a very vital role, and in this particular chapter we determined both theoretically as well as mathematically this molecular weight distribution pattern of both non-linear as well as linear polymer. For your convenience, we have listed several research papers as well as several books. You may look into all these references for your convenience and for the further study. A lot of things are there in these references. By this way, thank you very much for paying your attention.